Okay, hi pre-calc students. We are finally out of trig. We're going to start our next unit. Unit 10 is all about systems of equations, and eventually we're going to get into this topic of what a matrix is. And I'll tell you, matrices can be very useful in doing some things where you have to solve systems in higher levels of math. So not every high school in Monroe County teaches matrices. I think it's to your advantage that in Fairport, we give you a little bit of some exposure to matrices. So we'll be getting into matrices probably actually in tomorrow's lesson, introduce what it looks like, and just kind of the structure and how we can use it to solve systems of equations. And then after our spring break, whatever that might mean at this point, we'll be getting into some operations and some other stuff with matrices. So the notes that are posted on the website already are the filled in versions of what I'm going to run through quickly here about properties of lines to get started. This stuff is all from middle school up through geometry, and it's stuff that you should know already. So I figured I would just talk through some of the filled in notes real quick, and then if you guys have questions, you can pause, you can email me. If I go too fast or any of this, you guys should know what to do by now, but I will actually, by the end of this quick video today, do some quick sample questions with you on solving systems. So as far as lines go, some things that I'd like you to remember that we have this slope-intercept form, y equals mx plus b. Makes sense that we call it slope-intercept because we have m as the slope, and then b is the y-intercept of that line. So a quick example, y equals 2/3 x plus 1 would have a y-intercept of 1 right here. And if you think of the slope as the rise over the run, you would rise 2 and run 3 to get to another point on the line if we needed to graph it. So that should be all things that you're hopefully pretty familiar with. All right, beyond slope-intercept form, we have something called the point-slope form. And point-slope form is probably something you learn for the first time in geometry. I think it's actually really, really useful for some of the things that you would do in this unit, and then even beyond. When you write equations for some things in the study of calculus, having point-slope form available is actually pretty beneficial. So here's what point-slope form looks like. Y minus y1 equals m times x minus x1. M is the slope, just like it was in y equals mx plus b. But x1 and y1 are going to get replaced with any point on the line. So I think the advantage is that if I know a line contains a certain point, but maybe I don't know the specific y-intercept, we can use the values of that point, sub them in for x1 and y1, and just as easily represent the equation of that line. So for example, if I have y minus 2 equals 3/8 times x plus 5, that would be a line whose slope is 3/8 and contains the point -5, comma 2. Right? If you think of this x minus x1, if I do x minus -5, that's how you get x plus 5 in there. So hopefully that makes sense that the coordinate would be -5 and then +2. Two other quick notes about linear equations is that if you have y equals a constant, y equals some number, that would represent a horizontal line. We would say that that line has 0 slope, right? If you have y equals 0x plus something, that number that you're left with is going to be the equation of a horizontal line. If you have x equals some number, some constant, that would be a line whose slope is undefined at that point. All right, we have some relationships with parallel and perpendicular lines. Sorry, I'm still getting used to this camera thing, guys. I go one way and it goes the other. Okay. So for parallel lines, we should know that the slopes have to be equal. Okay, if you have a line with a slope of 1/3, to make a line parallel to it, you would also need a slope of 1/3. And for perpendicular lines, you would need the slopes to be negative reciprocals in order for the lines to be perpendicular. So if you have a slope of 2/3, then you would need a slope of -3/2 to make a line that's perpendicular. So then here's some quick practice questions. And again, this is all posted on the website. So if you just want to read through it, that's fine. But I'm just giving you some quick context for the practice here. Write the equation of line parallel to y equals -4x plus 7 through the point -1, 8. So if I see the word parallel, I know I have to keep the slope the same. Slope of this line is -4. To go through the point -1, 8, I think it makes sense to probably start with point slope form. Okay, y minus y1, y minus 8. would equal the slope, -4 times x minus x1. So x minus the -1 would become x plus 1 there. So if the question were to ask to leave it in, let's say, slope-intercept form, which is y equals mx plus b, we could do that kind of quickly by distributing the slope in. So that would make it -4x minus 4. And finally, adding the 8 to the other side will get you -4x plus 4 in that y equals mx plus b form. Unless it says to do that, I wouldn't. I would leave my answer just like this. Okay, but if it's at slope-intercept, we would do that quick converting by distributing the slope and then add that constant to the other side. Two other examples of this process we would have in number 2. Write the equation of a line perpendicular to y plus 4 equals 2 times x plus 7. And we want that to go through the point 6, -3. So if you're taking notes as you're going along and you want to pause it for a quick sec before I give you my explanation, go ahead and do that. Okay, so if I want to be perpendicular to this line through this point right here, really want to concentrate on that slope first. The slope is 2. So I'm hoping you're thinking in your head that the equation of a perpendicular slope would be -1/2, right? That would be 2 over 1. So I want a slope of -0.5 through the point 6, -3. So in point slope form, there we are. Y plus 3 equals -0.5 times x minus 6. This probably wouldn't be so bad either to distribute the slope in because half of 6 is a nice number. There's not a requirement that says we need to do that in this case. So you know what? This is acceptable right here. I'm going to stop with point slope form. Okay, last example in this section before I actually do some practice with you is I want to be perpendicular to this line, 8x minus 3y equals 7, through the point -2, 0. So in this case, you just have to quickly get y alone in this equation to identify the slope without showing the answer. It seems like the slope's going to be 8/3, right? Subtract -8, x to this side, divide by -3. So if the slope of this line's 8/3, perpendicular is going to be -3/8. I want to go through the point -2, 0. So you can see how I got that line y equals alone. Here's my perpendicular slope. So the equation would be something like this. Okay. So with y minus 0 here, you can really just easily express that as y, right? You don't have to do that. If you want to distribute that slope in, completely up to you, but like we mentioned before, not necessary to do so. Okay. So what we're going to do now is really talk about that end part of the notes. And this was a quick day of notes anyway. So if you're feeling like, hey, this is moving along pretty quickly, that's not necessarily a bad thing. Okay. I'm actually going to switch over and get some blank paper for us to finish this out and talk about some methods that we can use to solve systems of equations. So systems of equations, what we're going to see today are what are called 2x2 systems. A 2x2 system is when we have two equations with two unknown variables. So mostly x and y, right, that we're dealing with. So we're going to talk about the algebraic way to approach this. I'll mention graphically what's happening here as we solve the systems. And I'll tell you, there's two main techniques that you learn in algebra about how to solve systems. One of them is substitution, which will not be our focus in this unit. The other would be elimination. Elimination is nice when the variables are lined up like we have here. And the main idea would be, all right, let's pick a variable to eliminate. It doesn't really matter if you eliminate the x's or the y's as long as you do it correctly. And I'll tell you in this scenario, I think it's probably easiest to eliminate the x's because I can just multiply this bottom equation by -2. And that would make that a -4x, such that when I add the equations together, the x's get eliminated. So I'm going to kind of copy the system over here. Nothing changed about the first equation. Second equation would be the following. Make sure when you multiply everything by -2, you even distribute that across to the right side, right? It's like we're multiplying both sides by -2 with that step. So if you add the equations together, the 4x's go away. Done. And we get a total of -7y here would equal -1 plus -6 is -7. And then finally, divided by -7 gives us that y equals 1. Okay? All right, so once we know y equals 1, I have to go back and substitute that in to find the value of x. It doesn't really matter which equation we plug it into. If I plug it into the top, we would get 4x plus 3y, which we know y is 1, equals -1. So 4x plus 3 equals -1. Subtract 3 over to get a -4. And therefore x is -1. So we can express the solution as an xy pair, -1, 1. And I'm hoping what you're thinking is, hey, if I were to graph these two original lines, this result right here is the point of intersection of the graphs of those two lines, okay? So that's what we're finding graphically, but our focus in this unit will definitely be the algebraic approach, and we're looking towards this elimination process. Okay, here's another example. If we have 3x plus 2y equals 3, and 3x plus 2y equals -4. Okay, so if I want to solve the system, again, pick a variable to eliminate. Let's see, I eliminated the x's in the last one, so maybe eliminate the y's this time. So look at those coefficients of y. They're both the same, but if I add these equations together, I really want them to be the same coefficient, with one being positive and one being negative. So maybe I'll just take this bottom row and multiply it by -1. So leave the top equation the same. Now the bottom's -3x minus 2y equals +4. And if I do that, let's see, the y's definitely get eliminated. Those go away. 3x plus -3x. I don't know about that. 3x plus -3x, isn't that 0? So that's not what happened in the last case when I eliminated a variable. Here the x's also got eliminated. Some of you might have noticed that as soon as I wrote down this question that would have happened. Well, what's on the other side? 3 plus 4, which is 7. And last I checked, hey, Elodie, is 0 and 7 the same number? Are they the same number, 0 and 7? She's shaking her head no, guys. Nope. 0 and 7 are definitely not the same number. So therefore, this system has no solution. Why does the system have no solution? Well, first of all, because 0 does not equal 7. And also because if I look back to the original, thinking from that graphical perspective, these lines would have the same slope, right? Getting y alone. And if you have two lines that have the same slope, what's the conclusion? Well, two lines that have the same slope are parallel. And if I'm thinking about points of intersection, then there are no points of intersection if the lines are parallel. All right, we've got one more case to examine. If I have x minus y equals -3, 2x minus 2y equals -6, I'm going to decide, okay, which one do I want to eliminate, the x's or the y's? Maybe I'll go back to the x's this time. By the way, I think you're probably used to this, but there are certain cases where maybe we'd have to multiply the top and bottom equation by something to make those coefficients the same with different signs. You know, the ones that I'm modeling here, really, I'm only having to multiply one equation by something. Okay, the new system would be -2x plus 2y at the top equals 6. Distribute that -2 across. The second equation is now 2x minus 2y equals -6. Add them up. I was trying to eliminate the x's, I think, and oh no, not again. We've got 0 on this side. But what's different about this compared to the last one is, well, 6 plus -6 is also 0. Okay, so that's kind of interesting. So when we get 0 equals 0, it's not that there's no solution. It's actually, in this case, that there are an infinite number of solutions. Basically, any values of x and y that satisfy these equations, there's an infinite number of them that would work. So what's the difference between what we had in this case, where there was no solution, in this case, where there's an infinite number? Well, graphically, these lines were parallel, right? So there was no points of intersection. If there's an infinite number of solutions, what's the implication? If you actually get y alone in both, these are the same line. They didn't look the same, but they're the same with just a scale factor of 2 distributed in here. So that actually doesn't change the equation of the line there. They're the same exact line, so therefore, yeah, they lie on top of one another, and you get an infinite number of solutions. So that's really it for today's lesson. That was a nice and quick one, and what I'll tell you is that the homework is actually out of the textbook. If you don't have your textbook at home, I'll ask you to very kindly reach out. I'm sure you know someone in a pre-calc class somewhere, even if it's not somebody in our class, that has a textbook that you can have them send pictures of the textbook to you. But in section 6.4, you're going to try numbers 23 through 30. Those are the system questions like we just kind of worked on today. And then we're going to go all the way back to section 1.4. This is posted on the website, so you guys can check it out there. In section 1.4, you're going to try numbers 1 through 11 odd, and also 55 to 65 odd. That would be questions getting practice with the equation of a line like we did, kind of went through quickly at the beginning of the lesson. So if you have any questions about this stuff, you can send me a quick email. I'll get back to you. What I'll probably do is before starting tomorrow's lesson, I'll show you the solutions to the homework that I just wrote down here. All right? All right. So sorry, we're practicing writing the alphabet over here, guys. So, all right, we're going to get back to that. Hopefully you guys are having a good day. We'll catch you tomorrow.